Okay, so to help keep this moving a little bit quicker, I went ahead and worked through the last couple of examples that we're going to do in this section ahead of time, so we can just sort of talk through them. So we set up this example in the last video. We want to evaluate the surface integral of f.ds, where f is this relatively innocent looking vector field zi plus yj plus xk, and s is the helicoid with this parametrization. So we know that we're going to need RU cross RV, and so we computed those here. RU is equal to cosine of V sine of V0. RV is equal to negative U sine V, U cosine V1. Here's where I found their cross product. It comes out relatively familiar, sine of VI minus cosine of VJ plus UK. So what we said in the last video is if we want to find a surface integral over a surface of some vector field f dot ds like this, then we can change our integrand into f dot ru cross rv. So we've just found ru cross rv here. F in component form looks like zyx. So this is the dot product I'm performing. Now remember, zyx, we have to use the parametrization of our surface. So my x, y, and z components are given as u cosine of v, u sine of v, and v. I make substitutions for the z, y, and x here so that everything is in terms of u's and v's. This is the dot product I want to evaluate. Now when I evaluate it, I get this. V sine of v minus u sine of v cosine of v plus u squared cosine of v. And this is what I'm going to integrate. So according to our formula that we talked about in the last video, the surface integral of f dot ds over s, or across s, is the double integral from 0 to 1, 0 to pi. I'm using my, I'm integrating with respect to v first here. And remember, you can do either one first. Here's my integrand. Now, if you notice, this is a rather complicated integrand to deal with. I have v sine of v here. I'm going to need to use a product, or sorry, integration by parts here. Not a terrible integration by parts, but that's what it would require. Here, I could either use a u substitution, or I went the route of using a double angle formula. Sine of v cosine of v is equal to 1/2 sine of 2v, and I integrated that instead. And then here, this one's easy enough to integrate because the v is only present in the cosine of v. All in all, I get this as my integrand, this lovely thing. And if you evaluate this from 0 to pi, as complicated and as messy as this looks, the whole thing reduces down to just pi. Yeah, the u's actually disappear in this process. So that makes the rest of this a lot easier. The integral from 0 to 1 of the constant function pi du is just pi. Okay? So it would have taken me a lot longer to write all of that as we went along. Hopefully that wasn't too fast and that made sense. But again, go back and look at this example again if it's confusing. Okay, now in the event the surface, you notice we keep coming back and talking about this. If the surface S that we're integrating over happens to be the graph of a function z equals f of x, y, and if our vector field is given in this form pi plus qj plus rk, when we do this dot product, we showed previously that rx cross ry, which is the parametrization that we use for this surface, is going to be xi plus yj plus f of xy k. The rx cross ry that we've seen before comes out to this. When we take the dot product, we end up with an expression that looks like this, a scalar field that looks like this. So I'm not working through an example like this one, but basically this is just to show that in the event that we want to do the surface integral of a vector field across some surface S, and if the surface S happens to be a function of x and y, z is equal to a function of x and y, then you can use this as a formula to make the work easier. You won't need to evaluate any cross products directly, which can eat up some time. Okay, last thing I want to talk about in this section is just an application of surface integrals to something in physics called heat flow. So if you have a body, some kind of object, or it could be a lot of different things in 3 space. And if the temperature at any given point of that body is given by this function, u of x, y, z, then we give a definition to what we call heat flow. And it's defined as a vector field, F equal to negative K times del U, so the gradient of U. K is a constant. It's something that we call the conductivity of the substance, and it depends on the substance that makes up this body. But this constant is always going to be present here. The rate of heat flow across the surface S in the body. So if this applies to whatever the body happens to be, and if you define some surface contained in that body, then we can say that the rate of heat flow across that surface is given by this surface integral, where F is the function that we defined up here. Because negative K is constant, we can pull that out, and we're taking the surface integral across S of del U dot ds. So I want to do one example where we are we're trying to find the rate of heat flow across a sphere. So what we have here, the temperature at a point in a ball with conductivity K, we're not going to specify what the constant is here, is inversely proportional to the distance from the center of the ball. We want to find the rate of heat flow across the sphere of radius A with center at the center of the ball. So you have a ball, and then containing that is some sphere with the same center. First thing we need is our temperature function. So u of x, y, z is described as as being inversely proportional to the distance from the center of the ball. So if we place the ball where the center is the origin, that gives us the simplest case here. And inversely proportional means it's a constant divided by the quantity that it's inversely proportional to, which is, again, the distance from the center of the ball. That would be the square root of x squared plus y squared plus z squared, where x, y, z is whatever point on the sphere we're referring to. This is our function. I need the gradient of this function, and then I need to multiply it by negative k. I bypassed showing all the work here, but it's not hard to compute the gradient of this. It's just a little bit messy. It ends up looking like this, and when you evaluate the gradient, you'll actually have a negative x, negative y, and a negative k here, but by multiplying by negative k, everything is made positive. So I have k, my conductivity, times c, my constant of proportionality, times xi plus yj plus ck, all over x squared plus y squared plus z squared to the 3/2 power. Now the normal vector. So we came up with a couple of formulas for finding the normal vector, and this is a surface that's not a function of x and y. So I can't use the simpler formula that we came up with earlier. If you try to parametrize this sphere, we came up with a standard way of parametrizing a sphere in the previous section, in 16.6, using spherical coordinates. If you do that, finding this normal vector is a gigantic mess. It gets very, very complicated, and the determinant it's a beast to work out. You're more than welcome to try that if you want, but we can use a clever observation here to reduce all of that to essentially no work at all. Remember, we're talking about a sphere centered at the origin here. And one thing that we know about spheres is that the normal vector points in exactly the same direction as the position vector for a point on that sphere. And that's because the radius of a sphere is perpendicular to the tangent plane at any given point, meaning the normal vector will point in the same direction. So what does that mean? Well, if I pick a point here, x, y, z, then its position vector is the vector xi plus yj plus zk. Not only that, the radius of this sphere is assumed to be a, so the length of that vector would be a. The point of this is to make it a unit normal vector, so I need to divide by the magnitude of this vector, or that's the same thing as multiplying by 1 over a. So the normal vector is actually just this. It would take a very long time to get to this if we use just the parametrization of a sphere. But if that's the way you want to go for it. What we need is f dot n for the sake of evaluating our integral. So f is actually the function that we're integrating, which we're calling negative k del u. That's the function that we're going to use for heat flow. which is this guy. Notice these are the components up here, and then it's all being multiplied by, I back that up. This is just, this is our F. Yeah, sorry. So I'm a little, I'm tripping over my words. Anyways, I need to dot this with my normal vector, which I just found up here. Notice the 1 over a being a scalar, it's just going to put an a down in the denominator. And then dotting the vector here with this vector here is just going to give me x squared plus y squared plus z squared up on the top there. So this is what the dot product ends up looking like. These I can simplify. I just get the square root of x squared plus y squared plus z squared after reducing this. However, because we're talking about the sphere, x squared plus y squared plus z squared equals a squared. That's the sphere centered at the origin with a radius of a. This in here is just equal to a squared. So that greatly simplifies this. Square root of a squared is a. A times a is a squared. So this whole dot product reduces to like a constant, which is great. It's extremely useful that it does that. So if I want to get to the integral now, the integral over the sphere of f dot ds is the surface integral of f dot n. That's what we had worked out before. This f dot n we decided would be a constant kc over a squared, which we can bring out. And then I have the surface integral over s of ds. Now here is something that's important. We haven't mentioned this yet, but your book will mention it earlier in this section. We've seen before, anytime you're dealing with the integral of just d something, it gives you something that basically measures the size of the set you're integrating over. So to give you an example, if you're doing a regular double integral over some region D, and in here you have dA, the result of that integral is just the area of the region D. Well, the same thing happens here. If I take a surface integral over a surface S of this as my integrand ds, then the result is going to be the area of this surface. Well, we know what the surface looks like. It's a sphere of radius a, and we have a surface area formula for a sphere. It's 4 pi times the radius squared. So this surface integral I evaluate by simply using a geometric formula that I already knew. I get kc over a squared times 4 pi a squared. The a squareds cancel out, and I get 4 pi kc. That's the rate of heat flow. And again, remember, c is a constant of proportionality. We don't know what it is. K is the conductivity, which for a given substance, we may know this value, but for this example, we aren't given it. So this would be our final answer.